So good morning, everyone. So my name is Tian. So today I'm very honored here to present our work, and the title is Achieving Fairness Generalizability for Learning-Based Congestion Control with Jury. So in fact, the core idea of this paper is very simple. We want to imbue the fairness property into learning-based congestion control algorithms. So this research is a collaborative research between USDC and HKUSD. So let's get started. So first of all, I want to introduce something about deep reinforcement learning, or DRL. So this DRL have already been applied in congestion control in recent years. There's a brief introduction of DRL-based congestion control. So it in fact works in time intervals. So for each time interval, for example, like 30 milliseconds, the model will receive some packet statistics such as RTT and loss rate, throughput, something like that, and then it will adjust the congestion window or the passing rate in every time interval. And then a reward is calculated based on the metrics, network metrics, including throughput, latency, and loss. And then during the whole process, the objective, the goal of this agent or model is to maximize the expected cumulative reward during the lifetime of this flow. So I think the core benefit of DIL or learning-based methods in congestion control is that we can learn a control policy automatically and adaptively from empirical data without a lot of manual tuning. So one key objective in congestion control is fairness, right? So for fairness, we want to ensure that different flows can share the bandwidth equally. So we want to avoid having some flows monopolize the bandwidth and damage other small flows. So however, however, achieving fairness is in fact a very challenging problem in learning-based methods, because in fact, generally we train those DL-based models in a decentralized way, but in fact, you can see fairness itself is a global objective. It requires all the flows at the bottleneck coordinate perfectly to do it. So previous work have proposed to add a fairness metric into the reward function, ask the model to learn how to achieve fairness. However, this problem has this work have some issues. The learned convergence behavior may fail. It works perfectly in the training region, but it may fail when working under new network environments with different base RTTs or different random loss rates. So here we highlight this issue with the figure in the right. So you can see that if we add the fairness metric into the reward function and we train it under the network environments under the environments with 100 megabyte per second, you can see it can achieve near optimal fairness under that training environment. However, if we just put that model into another unseen network environment, for example, a network with 400 megabyte per second, you will see that the fairness breaks down. So here it motivates our definition of fairness generalizability, which means we want to get the ability to sustain fairness, across unseen network environments. Okay. So why previous work can only achieve have poor fairness generalizability? So we dive into this, and we have some core reasons. So in fact, I think we certainly think the core reason is because of those bandwidth related signals, which means those signals that correlates with bandwidth. So in fact, for a learning-based policy to achieve fairness, we have to add bandwidth related signals into the model as the model input. Here we explain it with this figure. So if you have two flows, a large flow and a small flow, if you want to you can observe the same congestion signals like in delay inflation or packet loss, right? So if we want them to achieve fairness, the larger flows have to need to have lower tolerance to congestion signals, need to be more sensitive, right? So therefore, it can relinquish the bandwidth to smaller flows. But the congestion signals they observe are in fact the same. So in fact, we have to put that bandwidth signals into the model input, so the two flows can differentiate their actions. So towards equilibrium point. However, this creates a new problem. So bandwidth related signals in Chen, because these signals in Chen environments may differ from those unseen ones. So you can see here from the table, showing the table, whether we are using absolute bandwidth features. For example, we use the throughput directly as the model input, or we use normalized bandwidth features. For example, the throughput divided by the maximum throughput observed so far, we can see that these values are different in training environments, between training environments and the testing environments, right? So in fact, consequently, the flow's behavior may become unpredictable in testing environments, making it impossible to ensure fairness in unseen network conditions. Okay, so here we have a code dilemma for DIL-based congestion control schemes, right? So on one hand, we must include bandwidth features to achieve fairness in one environment, but on the other hand, we have to discard bandwidth features to achieve fairness generalizability. So the IL agent is in trouble. Okay, so how to solve it? And our solution is that we need to decouple the task of ensuring fairness from the primary DIL task model. Okay, so the key intuition is to ask whether it is possible to introduce heuristics based on like network knowledge to constrain the policy search space to a subspace with early fair policies. So by doing so, the learning model will early search in this subspace with the for the base policy, and where you can only find those constrained fair policies. So we can ensure the fairness property during the whole training process. So this core idea, in my opinion, has a lot of potential to be, generalized to other learning methods in other system applications, where that requires specific properties such as stability or robustness. But here we are for fairness. So motivated by that, the key design of jury is in fact the introduction of an adapter to the DIL model. So we decouple the fairness task and delegate it to the adapter of this DIL model. So on one hand, we have the original DIL part, and this part it will already receive bandwidth independent features or bandwidth irrelevant features. So flows competing within the same bottleneck will only receive uniform or identical model inputs and generate the same outputs regardless of their bandwidth utilization. And on the other hand, we have the adapter part. For this part, we adopt a post-processing phase with bandwidth-related features. We use it to modulate the sending rate changes based on the flow bandwidths. Specifically, we want those large flows to act more aggressive, to act more conservatively, and those small flows to act more aggressively. So finally, we can ensure fairness. So in detail, jury works as follows. So for the signal collection part, begin with the raw network statistics. Jury will collect those action feedback features from the statistics, including the action it performs, it enforces, and the corresponding feedback from the network, including the change in throughput, RTT, and loss. And we can see we divided them into two categories. One category is bottleneck-related features. It includes the change of RTT and change of loss. In fact, we think these two features indicate the congestion level of the bottleneck, and all flows inside that bottleneck will experience the same values for these two features. So we will use these two features in the deep neural networks, in the model, and therefore all flow shoots output the same action, right? So for the output of this model, we instead of outputting a definite rate adjustment, we output a range, or action range, include the mean and the radius. So then we use those bandwidth related features we don't use them in the model, but we're using them in the post-processing phase. We use them to estimate the ratio, the flow bandwidth occupancy ratio. And then after we get the ratio, we use them to modulate the range and decide the final sending rate adjustment value. And we leave the calculations of how to calculate the ratio based on the delta of action and delta of throughput in the paper. In fact, this also forms the basis of PBR's fairness guarantee. So how do we get the final sending rate adjustment based? So here we have the formula based on the action range generated by the model and the ratio estimated by the bandwidth related signals. We get the formula to generate the final adjustment action. So the key takeaway of this formula is that if a flow has a higher bandwidth occupancy ratio, we want it to generate smaller actions, which means smaller rate adjustments. So finally, we can achieve. So now we can differentiate the actions between different flows, computing in the same bottleneck to finally promoting a fair equilibrium point. So in fact, you can see that Jury works more like a feature transformation or feature engineering trick over previous vanilla original DLL-based congestion control schemes, which makes it very easy to implement. So we implemented Jury using PyTorch with two fully connected layers of 1 to 8 dimensions. We integrated Jury into the Linux TCP stack, enabling real-time packet statistics collection and control actions via net link communication. And in order to and we train Jury in a limited set of network environments, so we can observe the generalizability of Jury across various network conditions. So here we evaluated Jury across diverse network environments. The figure on the right shows the average J index of Jury and the baselines across a wide range of network conditions. So the J index in fact indicates the fairness degree among competing flows. And you can see Jury achieves the highest score among baselines. And also the figure at the bottom illustrates the flow convergence process of Jury in different network environments with different bandwidths, base RTT, and random loss rate. So the results show that Jury can achieve both intra-environment fairness and fairness generalizability across various network environments and property. And I want to note that the property holds during the whole training process, which means even the model is not well trained, but the fairness property still holds because it is inherent in the model. So we also examined RTT fairness by introducing Jury flows with increasing base RTTs from like 70 milliseconds to over 200 milliseconds. And we can see that Jury still unequally share the bandwidth between with like negligible latency inflation, which means Jury also have very good RTT fairness. So we also tested Jury's friendliness to TCP by running it alongside a cubic flow under different base RTTs. So the flow ratio here was recorded across different base RTTs with a ratio of 1 indicating perfect friendliness to cubic. So we can see that Jury achieves higher throughput ratios than baselines while remaining more conservative than cubic. However, here I want to know that we do not guarantee like something like friendliness generalizability. So in fact, we think this is an open question because maybe we do not really want friendly generalizability because we cannot control other congestion control protocols, and they may fail in some scenarios, right? For example, like qubit will, as everybody know, qubit will fail or degrade under lossy links. If we blindly enforce, if we blindly want friendliness, and then we will also have some link underutilization. That may not be what we want. Okay. So to summarize, in this way, we identify the inherent conflict between fairness and fairness generalizability, and we propose Junxue, a simple yet effective method to decouple fairness enforcement from the DIM model. And our experiments show that Junxue effectively achieves both fairness and fairness generalizability. So that's all. Thank you for listening, and I'm happy to take any questions, and our code will also be released on the GitHub. Okay, thank you.
Okay. So questions?